Good morning, everyone. How are you doing? Welcome to Perception 2. So we got 5 really interesting papers this morning. Our first presenter, David Griesinger. Probably most of you already know him. He needs no introduction, really, but I'll just read a very short bio. David Griesinger, while he worked at Lexicon as a chief scientist for more than 30 years, he developed many products like Lexicon 224 Reverb, Lars Reverberation Enhancement System, and the Logic 7 Surround System. He has also worked as a classical recording engineer all life. His current work is on the mechanisms the ear and brain use to perceive sound, and how these mechanisms are affected by the acoustics in halls, operas, and classrooms of all types. So, David.
Thank you for the wonderful introduction. It's such a pleasure to see so many old friends here in the audience, and I hope you get something out of this. It's an old talk, actually. I'm recycling it with some new stuff, just because I thought the topic needs reawakening. I don't want to use the microphone. You're going to have to listen, okay? That's important. You know, that's part of the talk, really, but I'm not going to talk about, I don't know what to do. Do you have some assist? It's okay?
Just speak up.
Oh, I do. It turns out that when you talk directly to somebody, and the room is good enough that that's not muddied too much by reflections, they pay much better attention and they remember better. Whereas if I use this sort of thing, it's sort of God talking, and everybody ignores God. We know that. Okay, so low frequency envelopment in listening rooms. Is bass localizable in rooms? It's widely quoted that bass is not localizable in rooms, and that only a single bass driver is needed. The statement is true for continuous sine waves, but music is more than sine waves. It starts and it stops, and it fluctuates in pitch and rhythm. That's all very important. That's what you want to hear. Reverberation from low frequencies in music also fluctuates in time and space. The spatial effects of these fluctuations are treasured in halls. And they can be reproduced in back rooms, but it takes care. This talk presents a toolbox of methods that make spatial bass as beautiful in a playback room as it is in the hall. But first we have to talk about, is louder always better? Mono bass makes record cutting easier, blah, blah. The FM reduces the sideband power. These are obsolete technologies. We don't have to worry about this anymore. Loud bass can be achieved by putting your low-frequency speaker in a corner, but the bass can be very uneven. Welty et al. Use multiple subwoofers to widen the area where bass can be heard, but they throw away the stereo component of the low frequencies. It's mono. Stereo bass increases the area over which bass can be heard by exciting room modes that cannot be accessed by mono. Most recording studios have not been designed to make stereo bass audible. Recording engineers may have forgotten how good it can sound. That's interesting because when I walked in, I met Florian Kammerer, who was in fact just walking in. And he said, we always design studios with stereo subwoofers. We wouldn't be without it. So there's an exception. This talk is a plea for beauty in low-frequency sound. Are there any recordings with stereo bass? Well, I listened to an hour of Boston Popular Music Station while watching frequencies below 120 hertz on an XY oscilloscope. About 25% of the recordings had audible stereo bass, and some of them sounded really good. A great many listeners use headphones. Stereo bass can easily be heard. Stereo bass is essential in classical music recordings. Now, there's a very old paper, 1988, from Morimoto and Plosset, who just found that frequencies below 200 hertz, that's these, are particularly important for perceiving horizontal spaciousness. We've also found that capturing incoherent low-frequency reverberation that great halls provide is vital in classical music recording. As an example, we made a beautiful organ recording using a spaced microphone array, but the test cutting was lifeless and flat. We found out the cutting engineer had cut the bass below 200 hertz to mono. Recutting the disc, I demanded that, with full stereo, made the bass wonderful. Low frequency reverberation halls is beautiful. The Vienna Volksoper is a very dry opera house with little or no frequency reverberation. We were asked to demonstrate an acoustic enhancement system with full orchestra, with Steve here, who will confirm this if you have any doubt. Asher Fish exclaimed ecstatically, "Jetzt lebt der Ton!" as a pizzicato from the string basses danced around our heads like a flock of birds. All our electronic acoustic installations include multiple incoherent subwoofers. You really have to have them. This sound can be reproduced in a playback room. Now I'm going to talk about what happens at high frequencies, because that's really important too. The perception of envelopment above 200 hertz depends on stream formation, the process by which we separate individual sources from complex scenes. Okay, that means that you have to be able to separately detect the direct sound, because only the direct sound tells you where a sound came from, right? It also tells you how close you are to the sound. When you can detect it, you know it sounds near you, and you have to pay attention. We have found that foreground stream separation fails abruptly at a particular distance in rooms. We call this the limit of localization distance, or LLD. Sounds that cannot be localized in the presence of sounds that can be localized form a background stream. And that is very surrounding. I can't demonstrate this here, but I can with headphones or with my Crosstalk system, which I'll do outside later. When there are no localized foreground streams, we perceive only a single stream. It's a foreground stream. It's frontal, reverberant, but not enveloping. The difference is striking. I'm going to show you sort of what you can do. This recording... Okay, it's reverberant, but you probably can hear the instruments. You know, it's got a kind of clarity to it. This room is maybe a little bit too reverberant, but... Okay, this is mushy, okay, and that's because the instrument, you're behind the LLD, you can't localize the instruments, it's just a big mess of mush. If we play this with the crosstalk system like here, we did this in China, and it was very successful. I probably demonstrated to 20 people. There's a dramatic difference between F and K, listening to this thing. When you're in F, the reverb is all around you. When you're in K, it's all in front and kind of mushed together. It's quite different. With binaural recording crosstalk cancellation, we can instantly compare different halls and see these differences. Here is the Elbphilharmonic Hamburg. I was just there 2 weeks ago, and this is what I heard. I want to play the other one, which is a little louder, I think. So this is the Schemmerhorn Concert Hall in Nashville. Turn it up. that's the demos. Low frequency is spatialized a different way. It's not through stream separation. It's through a fluctuating ITD and ILD. When there are no reflection sounds below 120 hertz, you hear these. You hear directions just like higher frequencies. But when reflections arrive, they cause the ITD and ILD to fluctuate randomly. This is not a new thing. Fluctuation slower than 3 hertz are heard as movement. You hear it moving around. Fluctuation above 3 hertz make it just sound really spacious. And Blauer calls these phenomena localization lag. That's in his book. It's 30 years old by now. To hear low frequency development in a listening room, we must find a way to reproduce these amplitude modulations at the ears of the listener. Well, here's an example. This is a little clip from the Brahms Requiem. You can see in this part, there's fluctuations here at about 10 hertz or 20 hertz. And then here, that's more like 3 hertz. Both are really spacious. This is the phase response. I'm going to play a little bit. I've boosted the bass here 10 dB. Demonstration.
To hear the spatiality, we must make the phase and amplitude at the 2 ears different. We need to use the antiphase components in a recording to make the pressure at the 2 ears of a listener different. We need to create pressure gradient at the listening position. This requires exciting lateral room modes. In most rooms there are twice as many medial modes as lateral ones, and only the minima of lateral modes have high pressure gradients. The pressure gradients in room modes are at a maximum when the pressure is at a minimum. The gradient might be strong, but you may not hear it. We need to have just enough pressure from front-back or up-down modes to make the lateral gradients audible.
Speaker positions that minimize medial modes while maximizing lateral modes. If this doesn't work, use direct sound to create the bass. In small rooms, room modes are widely spaced and often well damped. Direct sound may be very significant, and low-frequency spatiality is often easy to achieve. Bass modes in larger rooms are closer together, difficult to damp with absorption. But we can attenuate them by putting speakers in positions where lateral modes will be excited and medial modes will be reduced. Contrary to usual practice, finding speaker positions that reduce the coupling to the strongest room modes can make bass both more uniform and more spatial. As another example, this is a room I was asked to work in at a music festival. It was a very small room, and it was set up like this, with the left speaker and the right speaker like that, and the mixer and the tape recorder like that. It sounded dreadful. So I changed the speaker position to this. This is at 1/3 the length, that's 1/3 the length. Listening position is here, and it really sounded wonderful. Why? You're moving the speakers closer to the listener. You're putting them in nulls of the lateral modes, the symmetric lateral mode. And they were also on stands, so they were in the middle of the upper wall, so that damps that first harmonic. Why did it work so well? Well, I just said all that, so I can skip it. Putting the speakers on stands also damps up and down. With this speaker arrangement, bass at the listening position is dominated by direct sound. It's like wearing headphones, and it works very well. I'm not going to go through these HSG slides, they're old. You find places in rooms where there's high envelopment due to a pressure gradient lining up with a pressure maximum from somewhere else. Square rooms are hopeless, definitely don't do that. If you have one, tear it down or put subwoofers here and here, otherwise you're not going to hear anything. This is my current listening room. I have, these full-range, wonderful speakers by Alan Devanche here. This is a 15-inch, 2,500 watt subwoofer. Works very well down to 20 hertz. But there's also some side speakers, okay? So just for fun, I turned off the Logic 7, and I tested for bass spatiality with just the mains, and it wasn't very good. So I tried moving them forward to here, which puts them at the null position of this mode. And goddamn, it worked. I get a huge pressure gradient at the listening position, but you can't hear it because there's no pressure there. You need a combination of modes to actually hear it. So I put them back where they were. But the interesting thing was, let's see, do I have this here? No. I added 2 powered subwoofers in parallel with the front at the sides of the listening position, 12 feet apart. It was great. The bass was rich and enveloping. And these things are cheap. If you don't have one, spend $300, go buy one. It's worth it. Okay. So I turned the extra subs off and turned Logic 7 back on. And the side speakers go down to 40 hertz. That's these guys. And it sounded great. Not as good as with the subwoofers, but it was good. Well, how can you test your system for low-frequency spatiality? Okay, good question. Say you want to know, is my system good or bad? What do you do? Well, Plusl, in the first paper I showed, used broadband noise, or octave-band noise, and it really doesn't work very well. So I invented, or just decided to use this signal, which is wonderful. If you take a noise band and you narrow filter it, so 10th octave or tinier, what you get is something that sounds like a tone, but it wobbles at a 5 hertz. It wobbles at a 5 hertz rate, and that's right in the middle of Blauert's range, 3 to 10 or 3 to 20. Okay, so it sounds great. So here it is 63 hertz wobbling. Is it moving around the room? Right where I am, it's not. It sounds pretty mono, but that's, rooms do that. So if I play it in mono, all right, so this is 100 hertz. That will be. And if I play, see, it's not moving up here. Okay, let's try down here. Okay, well, you shouldn't hear a little bit, it's mono. But anyway, it must be some interesting effect. Huh?
The buzzes.
Oh, the buzz is moving around. Yeah, that could happen. The distortion is different frequencies. Anyway, so the nice thing about this is I have a CD which has these in 3rd octave increments, and you can just play this and say, well, this one's really spacious. This frequency's not. What do we do about that? Maybe we should try something. You know what I mean? So that's a kind of neat way of doing that. Well, what happens if you turn your head? I've been talking about lateral energy as if the person was always looking forward, right? What happens if you do this? Well, it's all gone. It's a whole different situation. Then you need something going this way, right? And if you're just listening to music walking around the room, you don't want this to happen. You don't want it to be spatial when you're facing forward and not spatial somewhere else. One of the advantages of these kinds of old-fashioned surround systems is that you can make spatiality in all directions work, if you're lucky. Conclusions. And there's going to be time for questions. I hope there'll be some. Envelopment, the perception that you're surrounded by a living 360-degree spatial reverberation, is possible to reproduce in a listening room. In small rooms, 2 loudspeakers can do the job, at least if you're facing forward. But they must be carefully placed, ideally along the longest wall near the 1/3, 2/3 of the width. Putting them near the short wall is disastrous for spatiality. Larger rooms can be spatial also, depending on their dimensions. If you have a square room, tear it down or invest in stereo subwoofers at the side. Logic 7 was invented in part to help create an enveloping low-frequency bass sound throughout the room. If the side speakers are nearly full range, it can work quite well. It can work quite well anyway, actually. But it's an idea that, maybe having good low-frequency response at your side speakers might be helpful. Okay, now we have plenty of time for questions, so I spoke way too fast.
David, I have a question.
Yeah, go ahead.
Have you also looked at the effects of vertical low frequency decorrelation on the low end?
I have certainly not looked at that.
Okay.
Tell me about it.
Well, no, there is, evidence from Humcook, who's just standing up now, that in the vertical plane, it is by far not as effective as in the horizontal plane.
Well, I would have guessed that.
Yeah. So I just was going to be interested if you have also any experience on that.
Well, what we found is below 500 hertz, there's no effect of decorrelation in the vertical, but above that, there's slight difference. Yeah. Of course, you can perceive
I
slightly
haven't
more.
said anything about vertical, but Steve might have something to say.
I was going to say, we do enhancement systems all the time, and we're putting subwoofers vertically in the ceiling. You have to diffuse things across the room and maintain uniformity. It's the only way to do it.
Well, I would comment on that, and I don't want Steve to contradict me, but he might. I think when you're working in a large hall where there's balconies and things like that, you really need that because you want the bass to be as good everywhere as it is in front. But the human ear is very insensitive at low frequencies to the direction of low frequency sound in the vertical plane. It's all done by pin effects, which start at about 1,000 hertz. It's a big a kind of issue of laughter to me when you see these full-range speakers on stands as height speakers in Oro or Dolby kind of setups. You say, why are they doing full range? You can't hear that. You know, if you had a speaker this size that reproduced nicely above 800 hertz, that's fine. Your ear can't detect height. You want to say something?
Yeah, I mean, thanks. An interesting observation. When I fooled around with this some years ago, and when we were interacting more, and I looked at the stereo content of several different tracks, including some that you sent me. And one interesting thing I found was that if you looked at it on a time-varying basis, I found that at the points where the signal was the highest, the decorrelation was actually less at those points, and that a lot of the decorrelation was occurring when the signal was actually at low signal, so at low level. So if you just kind of average it, you might miss that this decorrelation is not just constant over time. Of course, it varies, and that I'm wondering whether when you calculate the stereo, the decorrelation or whatever in a signal, do you just average it, or do you take that into account, or?
I don't think I calculate the decorrelation in the signal. I think I listen to it.
Right.
And I guess I take it into account.
Yeah.
and it's interesting that you think that as the music gets louder, the decorrelation changes. That probably has to do with the instrumentation, I would think. Or if it's been a pop, it's how it was recorded.
I don't know why, but I'm talking about short-term, instantaneous changes, not like turning the volume up, but I don't know why that is. That would be a good question for you, because I don't know.
I would have to look at it. I don't know either. I had a suggestion for you, though. I think your system is great. You do use just the L plus R component. At least that's my understanding. That's fine. Why don't you do that? But you could do it separately so that you could take the L minus R and put it laterally while leaving your L plus R the way it is. I'd love to hear what that sounds like.
Don't you have a patent on that yet?
No, that's for you.
Okay.
I don't need no patents.
Any other questions? Can I ask one question?
Sure.
Yeah, I'm really interested in your spatial impression paradigm from your old papers. Early spatial impression, continuous, and background spatial impression, which make
Well, that's what
real
I was
sense.
just saying, but I used different words.
Okay.
You have the foreground.
Yeah, so in your paper, you describe CSI, continuous spatial impression, which happens during the ongoing part of the sound.
Yeah.
It doesn't really produce much envelopment, but you have stronger envelopment in the BSI region after the offset of sound. So I just wonder if you tested this method using different types of signals, like transient signals, ongoing signals, and how the impression changes depending on the
I think
time.
about it very differently now. Okay. And I'm really a disciple of Bregman, if you will. That I think that the way the brain processes sound is to try and find sound objects or streams as independent from each other and as independent from noise or other problems in the room that might be there. So I think the brain is always looking for first the closest sounding sound, which has high priority for listening. And the only way you know that a sound is close, really, is by detecting the direct sound. Mm-hmm. And I didn't put the slide in for this is a different talk. But it sounds like my speech is created by pulses in the vocal cords. Okay, bink, 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 bink at the fundamental frequency. That makes amplitude pulses in the waveform, which extend as high as you can hear. That's actually in Blauert's book too. But the ear uses those pulses to separate one sound from another. If the pulses are regular, the ear knows that's direct sound. Because when reflections come, they become irregular because the reflections come with time delays and mess everything up. Okay? So the ear is interested in regular pulses, and that's what a foreground sound has in it. And you can time those pulses and find ITD over the whole, which is how you can localize. Right?
Yes.
So that's the foreground effect.
Yeah.
Yeah.
My question was, maybe, the ITD fluctuation, this fluctuation rate above 3K gives, not 3K, 3 hertz, gives, spread impression or envelopment or source width, whatever we call it. Right. But is it really audible during the ongoing part of the sound? Like, for example, if you play orchestral music, which has a lot of, ongoing sound. So unless you hear kind of discrete offsets, can you really hear this effect in the middle of all of this? You can. Okay.
The thing about bass is you can't separate bass notes from it except by pitch. Okay? Yeah. There's no pulses you can use to get at them. And you don't know what the direct sound is because there's no way of telling what you're hearing is direct or non-direct. Okay. So what matters is this sense of movement that happens. That the overall sound seems to be swimming around. Yeah. And you hear that as low frequency envelopment.
Great, thank you. I should try this. Thank you.
Okay. Yes.
When you're interfacing subwoofers, do you use high-pass filters, and how does that affect the envelopment of the low end?
I use low-pass filters. Yeah. When we did the MC12, I insisted that there are crossovers. I think they're 12 dB per octave. And they're phase linear, so that there's no interference in the crossover region between the subwoofer and that's actually pretty important. But yes, we split the bands. Yeah. Do you have to? Actually, no. I mean, when I did this little experiment in my listening room here, I just put the subwoofers here, and they're just standard JBL subwoofers with a low-pass filter. And I adjusted that to maybe 110 hertz or something like that. It worked great, And then I left these on. You weren't hearing them very much anyway, so, at that position. You do hear them at 20 hertz, though, when they kick in.
With your main speakers, you don't filter that?
I didn't in this experiment. It seemed to work fine. In the MC12, we did cross them over, yeah.
I'll go again.
Yeah.
I remember you explaining this to me some years ago, and I didn't quite get it done. I still have a little trouble. That one of your main premises that you want to have you want to be at a null so that you have a phase shift across the ears, but you also want to have another mode which is providing pressure. But it seems to me that if anything, that would be counterintuitive because that would tend to swamp out the phase differences.
Depends on the strength.
What's that?
It depends on how loud it is.
Okay.
Okay, you just need enough so that you're aware of that lateral sound. Yeah. And I've not gone around, measured that, and calculated anything, but you can move around the room and see that happening, or rather hear it.
Okay.
Yeah.
I think we have time for one more question. Yeah. Okay.
And how do you feel about actually having the subwoofers actually directly mounted to the floor system, or actually using spikes or any other ways of?
I'm not a big fan of that sort of thing. In fact, if I had my druthers, I'd have the subwoofers up on stands. That's what happens in a small room, where you really want the low frequency driver to be at the null of the ceiling floor mode. And putting them on the floor, what you're doing is maximizing these up and down modes. Now, in HSG, we had drop ceiling with fairly high absorptive panels, So that wasn't the problem. We could have the subwoofers on the floor or in the middle, didn't matter at all. But in a room with a fairly high ceiling that's hard, it's going to be problematic. There was at HSG in Northridge, there was a demo room for consumer equipment. It had hard plaster, hard floor, no rug, hard walls. I couldn't make anything work in that room. It wasn't just the up-down modes, it was all the cross modes. There's all these different cross modes that go kitty corner around. This room didn't damp any of them, and it was horrible. Couldn't do anything in it. Yeah.
Okay, so